Hi, so I just came across these. These are some custom LED assemblies I designed for a big lighting installation last year, and I thought there are a few construction techniques that I thought might be of interest. So I thought I'd just run through some of the aspects of the design of this thing. These were designed to go inside some acrylic cubes which had sort of diffusion on the outside, and there are three different sizes, 6, 8 and 10 inch cubes. These occupy about sort of 2/3 of the length of the side of each cube. Now unfortunately I don't have any of the acrylic cubes here. Those were fabricated by my customer in the US. So I've built this highly sophisticated 3D model to show how it all fits together. So we've got the LED assembly in the centre. Say that they were cubes, so the bottom edge would be about here, and we spent quite a lot of time experimenting with different LED layouts just to get nice uniform illumination on all 5 sides. These were hung on steel suspension wires. They had, I think, about 2 or 3 cubes per drop, but only one of the cubes in each drop actually had LEDs in it. The rest were just dummies. The power cable sort of ran down the suspension wire. I think they actually put some heat shrink sleeving on it to fix it. So that sort of went down like this, and then there was enough slack on here so you could actually pull the connection out. So yeah, the reason this is at that angle, it just to allow a certain amount of curve on the cable whilst keeping it fairly well hidden, so the cable sort of stays fairly flat against the PCB, but there's enough length to be able to unplug that connector and plug it in at installation time. Now the way this all went together, at the bottom I think they had some sort of small gland or gripper detail. I'm not sure exactly what they ended up. I don't think I ever saw the final version they used, but the idea was that the bottom hole was sort of held central and also provided retention, so that actually that's what actually physically held the cube up and stopped, held its vertical position. There was just a sort of gland and I think some sort of end stop on the bottom. Then at the top we have this sort of relatively large hole, so obviously this sort of flops about a bit in this configuration before the LED assembly gets put in. The LED assembly's got these sort of slots at each end, so this gets just slotted onto the cable, drop down into the cube. Then we just use 3 plastic snap rivets, 2 to fix the PCB into the cube, then a third one here which just locks the position of the drop cable, so this now can't move. We just got like a single hole for the drop cable to go through. So this now sort of stays vertical because now we've located the drop cable at the top, so this all just stays all nicely together, so the PCB is actually acting as part of the mechanical assembly, and that worked really nicely. Incidentally, these plastic snap rivets, I'm actually quite surprised how often I sort of mention these to people and they've not seen them before. They're just a really simple thing. There's just they're a 2-part thing. They come like this. There's various sort of lengths and diameters, and so as you push these down, this unfolds, and yeah, they're really useful in a lot of cases where you might think about using screws. They've actually got a lot of advantages. Obviously they're a lot faster to install. They won't ever work loose, but also you can insert them from one side, so obviously much quicker to insert than a screw. The other nice thing is because they're plastic, if you're going into a PCB, you don't have to worry about keeping tracks clear of the hole as you would with a metal screw that might make contact with the PCB. Probably the only downside is they're a little bit fiddly to undo, in that you basically need to sort of get a sort of fingernail or something under it and actually pull the centre part out a little bit before you can pull the rest of it out. But apart from that, yeah, a lot of the times they actually have a number of advantages over nuts and bolts, and they generally come in black and white. I'm sure you can get custom colours if you order enough of them. Obviously I think we use the white ones on this installation. I just only happen to have the black ones to hand. Now, one of the things we spent quite a lot of time on was getting sort of quite a uniform illumination of the cube, sort of making it look as symmetrical as possible. Now, the first thing towards that was to use the choice of LEDs. These are Osram Duris S2 LEDs, and the nice thing about them they've got phosphor. The whole top is made of the phosphor, which means they've got an extremely wide emission angle. So even if you go pretty much, right to 180 degrees, they're still actually kicking out a reasonable amount of light. So a lot of LEDs have maybe, sort of 150, 160 degrees, so you'd get a sort of dark section here, but these actually put out enough light on the side that you actually get, by sort of playing around with the spacing, you actually get fairly even illumination if we'd used narrow angle LEDs, we'd actually got quite a big sort of dark shadow coming out on this angle. But in fact, if you look, it's almost the opposite. We've actually almost got more light coming out of it here than we have off the face, so we don't have a great dark spot. And we started off with basically having this parallel to the face of the cube, but we actually found that rotating it 45 degrees was a little bit more effective, because sort of the bulk of the light was sort of coming out sort of in this direction. So if we fired that towards the corner, because obviously the corner is further away, and as the level drops off towards here, it gets closer, and that actually balanced out to some extent. There was another effect. We found that there was a very slight, not so much a darkness, but just a slight discontinuity on this angle. So I can't actually remember whether we actually ended up having it square in the cube or at 45 degrees, because there was a bit of a trade-off. One gave more even illumination, but at the expense of having a slight discontinuity on the face, and the other, we sort of the discontinuity was towards the corner, which obviously is also a bit of a visual discontinuity anyway. So I can't actually remember which way we ended up, but there were pros and cons of the two solutions. And it's certainly the first thing that was non-intuitive is that actually having this with the corners going to the face actually gave probably the most uniform illumination. And we also found that we originally didn't have this end fill here, but we found that the bottom was a little bit too dark, so we added this board just to push a bit more light downwards, although we get a certain amount of reflection down. The other thing which complicated things was that you get a lot of internal reflection, so that this is firing at the side, but a lot of that light then gets bounced off, so we get some of that gets bounced off onto the bottom face, and without this that actually caused the bottom to be a little bit dark in the centre, so we needed to add this extra board just to fill that in a bit, to get more uniform illumination on the bottom face. This is electrically a very simple assembly. It runs on 24 volts. We run these from my 48 channel dimmers. I've done a video on these before. So we've just got strings of 6 LEDs with a couple of series resistors in each chain. So this has got 2 chains of 6. Each chain of 6 is 0.3 watts. There's the LED coat's about 50 milliamps per LED, and these are on aluminium PCB to get good heat dissipation. Obviously inside the cube the airflow is limited. Obviously we want the cubes to be sealed so they don't get full of dust. So these are not designed to run continuously, and you can see from the I'll link to the video of the actual content. The idea is it's sort of moving patterns throughout the thing, so the duty cycle on these is fairly low, so thermally this worked out quite nicely. But so we use the aluminium just to spread the heat out and get the heat away from the individual LEDs. But the aluminium actually gave some really nice advantages for assembly. The first version of this, we didn't have the bottom infill board, so we just had sort of these 4 aluminium PCBs. And one little detail that I come up with fairly quickly is to actually hold this thing together is you could actually put a tab on the aluminium PCB and just give it a 45-degree twist to actually lock it together. And the first version we had this detail on all 4 sides. One problem with that was it was actually quite fiddly to assemble, because you actually had to sort of plug all the boards in and then sort of line them all up and then sort of plug them on the top. And because this was being installed in the US and the people doing the structural fabrication were in Canada, these are actually manufactured by a manufacturer in Canada, so I was having to deal remotely with a subcontractor assembler. So I wanted something that was like super easy to assemble. One of the issues with something like this is if it's something a little bit unusual that an assembler thinks might be a bit fiddly and complicated, they are likely to sort of pad out their quote quite significantly, because if they don't quite know how long it's going to take to assemble, they're going to play it safe and sort of charge what they think it's going to take, despite the fact it's actually quite a simple operation. And this was an earlier iteration of the end fill. When we figured out we needed some end fills, this was one of the earlier versions, and here we had another one of these edge connector plugs connecting up to here. But again, this still had the problem of having to sort of slot all these through in one go, which was quite fiddly. We also found that we actually wanted the end fills to be around the outside rather than the centre. That was a bit more effective. The solution to the fiddliness was to well, actually there were 2 issues here. We needed the LEDs near the edge to get the right fill factor, so that meant we couldn't really put these connectors on the edge because they just got in the way. They took up too much space. So we added another central piece. So this is just literally a connector piece. All it's got is a couple of resistors. We actually had resistors on here and here, partly so that we could burn off some of the heat on here, because this is a fiberglass board rather than aluminium, because these actually run at significantly lower power than the other LEDs. But also in terms of panelisation, I'll get onto that a bit later, but there were reasons why we made these two end boards fiberglass rather than aluminium. But basically what I did was add this extra board, and obviously this is all on the same panel, so adding this didn't really cost a huge amount. And instead of having these passing through, we just had like a locating pip. This makes assembly a lot easier, because we can actually, because we've got just this centre one higher up than the rest, we can just locate this one first and then just slip these ones in one at a time, because it's only a locating tab. These snap in quite easily. Then when they're all in, all we need to do then is just give this a twist, and that's now all held together quite nicely. So yeah, no additional fixings, it's all done. And say that little twist detail on the aluminium PCB just makes this whole thing go together really quickly and simply. These connectors, these are made by AVX, who make all sorts of really interesting connectors for connecting PCBs together. It's their 9159 series. There's actually quite a lot of different connectors. I think from memory these are 9159, 551. They do these in a few different numbers of ways. They also do through board and surface connectors. The surface ones come with a tab for picking up on the pick and place machine, and obviously the through board ones come taped upside down. They're basically the same connector. There's just a very slight difference in the way they form the leads, so that the through board ones just drop down onto the PCB. So there's quite a lot of flexibility for plugging PCBs together in various different permutations. Another nice detail is they've got this stepped entry, which means you can use either 1.6 or 0.8mm PCB with them. For a 0.8 you just make it slightly wider so it fits into this outer slot. One thing I didn't want to do is have this sort of clamping force actually putting force directly on this connector, just for robustness. So what I did is I actually put some sort of landing feet, so these feet actually land on the PCB and actually define the position and geometry, and there's just a small amount of tolerance gap here, so that when this is plugged in, the bottom of that tab is maybe perhaps 0.5 millimetre out of the bottom of the connector, so it's not putting any strain at all on the connector body. All the force is taken by these feet landing on the PCB. Similarly at the top, where it passes through the top, this ledge is what actually sits on the PCB, so that when you're twisting this, all this clamping force is not putting any force at all on the connector, because there's just a little bit of a tolerance gap on the end there, just to avoid stressing the connector. Obviously that's more important on the through board one, where if any force on that would just pop that up, and that could pop out quite easily. So it's quite important to make sure you've got the right amount of clearance in there just to allow for that. Now these are all, we had 3 different sizes of these for 6, 8 and 10 inch cubes, and the installation was all pre-designed, so we knew exactly what proportion of strips we needed. So I spent quite a lot of time trying to design a panel to get the right proportion of strips on the panel. Unfortunately they changed the design later on, so I think we ended up with a bit of a surplus of one particular strip, but I spent quite a lot of time just juggling the panel size versus the proportion of each of these types of strip on that single panel, because obviously we wanted to keep everything on one panel to reduce the tooling costs for stencils and for setup. So here's the actual final panelisation of this. So you can see there's the various different types of strips arranged to get as close as we could to the right proportion. So this was quite a lot of spreadsheeting just to play around with the different proportions of strip sizes on the panel. Now on this bottom board, this is a very simple circuit. It's basically 24 volts in, but because it wasn't designed to be able to run at 100% duty cycle, we needed some way of making it, although the content will be designed to not run any particular fixture for more than a certain amount of time, we couldn't really predict reliably exactly where the point is where they got too hot. So there's actually a thermal limiter circuit on here, And of course what you don't want is for the thing just to shut off. You know, if it gets too hot you don't want it just to shut off. So this actually is designed just to back off the brightness as the temperature increases, so even if it does go into that region it would almost certainly not be noticeable at all unless it was like vastly overloaded. So it would just slowly back off. I'll go into details to how that works later on, but that's a very simple, very cheap circuit, but that worked quite nicely. Just going back to the manufacturing side, so all the aluminium strips were done on one panel. Then there was a second panel which was for these two boards, and again, because we've always got a 1-to-1 ratio of these boards, it makes sense to do both boards on the same panel, again to reduce tooling and stenciling costs. And so these were both done on FR4. This one has to be on FR4 because we've got a connector on this side, and you can't really, you can't do through-hole components on aluminium, because aluminium is basically a very thin insulating layer, then the layer of copper, then the resistor over the top of it. I believe there are processes for doing things like through plating, but it gets a lot more expensive. But because you've got the aluminium conductive substrate, you can't put through-hole components on there because they'll just short on the aluminium. So this top bit had to be done on FR4 because we've got this through-hole connector on it. You know, we had to have it connectable from the top, so there was really no choice about doing that, I suppose. And it might have been possible to use like the through-board versions of these connectors, but it didn't seem to really make a lot of sense to do that. And this one basically got put on the same panel primarily for panelization reasons. It would have been quite difficult to firstly to panelize this on the same board as these purely for efficiency reasons, but also the whole business about getting the right number of these strips on a panel. If we'd also have had to have got the corresponding number of these, it would have been even more difficult. So it's much easier just to do these on a separate panel, because the lead power on this is a lot lower. This didn't need to be aluminium, and this could have been made in aluminium. You can see there's actually there's just sort of single plane on there. That's really for thermal reasons. There's actually no electrical function at all. This is a purely single-sided board, so this could have been done on aluminium, but it actually made more sense to do it on fiberglass. The other reason is for separation. This was done as primarily as a V-scored panel. There is a bit of routing, but it's mostly V-scored because obviously they're rectangular strips, so they just snap apart. Whereas here we wanted to keep this profile as tight as possible to avoid any shadowing, so we'd have needed quite a lot of routing if we'd have done that on the aluminium. So these are just both done on fiberglass because it just made sense from the production point of view. And one reason we've got resistors both on this vertical section which powers this and the top board. This was really so we could adjust. These weren't both manufactured at the same time. It meant that we could assemble the entire panel with all the same resistor value to minimise the bill of materials. Then we could use this resistor value to tweak the how much dimmer these LEDs were relative to that one. Just to give us a little bit more control. I have a feeling we actually that panel went into production before we'd finalised the component values for these LEDs. We knew they'd have to be dimmer, but I don't think we actually knew exactly how much dimmer. We were still waiting for some more cube samples to be manufactured. So by putting a resistor on here as well, instead of having all the resistance on here, meant that we had that scope to adjust this when we pressed the button on production on these top PCBs. So this is the protection circuit. And basically what this is doing is when the thing's below a certain temperature, just turn everything on and basically not do anything. But as the temperature increases, it wants to start PWMing the LEDs to reduce the overall power to get the temperature down. Obviously, as the temperature continues to rise, the duty cycle will get lower and lower until it will hit an equilibrium. Now, obviously, this thing is being powered by the output of the dimmer, so its input supply will be PWMing on and off at 250 Hertz. So this frequency that this operates at needs to be sufficiently higher than that we don't get any issues like beat frequency. So for example, if it's only running at say 3 times that frequency, as the limiter starts to take effect, you might get some beat frequency effects that cause visible sort of strobing. So this is actually running at about 25 kilohertz. And the reason it's that high is primarily, there's two reasons for it being that high. One is so that the number of cycles is significant within each PWM cycle of the incoming supply to avoid that strobing, but also I always like to keep stuff out of the audio band because LEDs can sometimes exhibit some slight microphonic type effects and produce audible noise in certain circumstances. So we've got the 250 Hertz incoming PWM, and that will then produce something of the order of 100 cycles if this limiter is actually in operation. So this is very simple, very cheap. Obviously you don't add any too much complication to a circuit that's most of the time it's not going to be doing anything. It's based on the LM393, which is a dual comparator. The one nice thing about it is it will run up to 36 volts, so this can be powered directly from the 24 volt supply. There's a reverse polarity protection diode there. We don't need that for the LEDs, because obviously the LEDs are, if you reverse the polarity for these LEDs, they just won't come on, so we don't need to pass the full lead current through the diode. So it's just a small diode on there just to protect here in case there's a problem with the wiring and someone's wired something up back to front to avoid melting this. So the first stage, this is just a 25 kilohertz oscillator. This is the conventional comparator oscillator. You see these, you can build these with comparators or op amps running as comparators, and it's just a sort of fairly basic square wave oscillator. But we're not actually using the square wave output, we're actually using the voltage across the capacitor, which gives a triangle-ish waveform. We're then feeding that into a second comparator with a reference voltage derived from the temperature. So we've got the thermistor, and the resistance of that thermistor was chosen such that when it's below a certain temperature, I can't remember, I think it's something of the order of somewhere between 60 and 70 degrees from memory. I can't remember what it was exactly. Obviously this thing is sitting this way up, and the thermistor is here, so that the heat from there, we'll get the heat rising. So a lot of the heat that's coming from there will hit this top board. We've actually got some obviously conduction through these where the boards hit on there, so the temperature of that thermistor will track the overall temperature reasonably well. And so as that temperature increases, the resistance of this thermistor increases, and therefore the voltage at this point increases. So for example, at very low temperatures, we've got a high voltage here, so our slicing level is here. So the triangle wave is always below this reference voltage, and therefore the output is just high all the time. As the temperature increases, this starts reducing, and we then start slicing this triangle wave to that, which will then produce our output PWM. And the further this goes down, the wider this gets, and the more off time there is. And incidentally, these comparators have got open drain outputs, hence we've got a pull-up resistor here and a pull-up resistor here as well. We've also got this second resistor which acts as a divider, so that this will only go up to 12 volts to protect the gate of this MOSFET, and this MOSFET is what turns the LEDs on and off. One thing you might notice is that this has got 8 resistors, and they're all 10k. Now, there's a very good reason for this, and again this boils down to cost and complexity. Resistors cost almost nothing, but the cost to place that resistor on the board is significant. It could, depending on your manufacturer and the quantities, you could easily be looking at maybe even somewhere like maybe 5 to 10 cents to place each resistor. So what I typically use in this scenario, these 4-way resistor networks, which they cost a little bit more than individual resistors, but the reduced placement cost far outweighs that. So if you can get your resistors all the same value and soak them up into these resistor networks, then that just helps get your cost down in terms of placement cost, and maybe also bill of materials. If you can get, for example, let's say you needed lots of 20k, lots of 10k resistors and one 5k, it might be worth just using two resistors in this resistor packet in parallel to get that combination, just purely to reduce the number of parts you're placing on the PCB. There's another couple of little details on here. Now, as I mentioned, this was being manufactured by a subcontractor in Canada, so we needed a way of testing these easily, again with some very simple instructions. So these test points are actually connected across the thermistor. The test procedure was simply, firstly, just power the whole thing up and check that all the LEDs are on, which this is a fail because these ones aren't. This board's been bashed about a little bit, so we have a fault there, but let's pretend that's not an issue at the moment. And so the test procedure was first power it up. We specified a lower voltage just because if you power this at full voltage, it's just, you start needing a welding mask, it's ridiculous. So we said, okay, test it at like 18 volts or something, just for comfort more than anything else. And at this stage, all you're testing is the fact that everything is soldered properly. So that immediately says that all the LEDs are working. And to test the limiter circuit, all you do is you just take a 10k resistor, connect it across the test points, and observe that it goes dimmer. It doesn't go off. It does change, but it doesn't go off. So this effectively tests this entire functionality, because any open circuit here that meant that, if for example some open circuit that meant that the LEDs were on and the limiter wasn't working, so what you're simulating is literally that thermistor going down in resistance, just to show that pretty much everything is functional. The other thing I put on here was this was just a solder bridge, so that if there was some issue with this limiter, maybe it was cutting in when we didn't want to it, we could potentially put a solder bridge on there just to completely bypass it. And again, that was done on the put on the top. It was put on there so that could be added on the assembly without taking these off, but also potentially could be even done after the thing had been assembled. It was just a sort of contingency. Yeah, you've only got one chance to get these things right, so anything that might go wrong, you've got to, you know, it's always good to put a few little fallbacks and contingencies in there to deal with any issues, so that, you know, if for example we did have an issue with this limiter tripping in too early, we could do a sort of emergency fix by shorting that, or potentially even putting a resistor across here to bias the thermistor slightly if it was maybe not cutting in early enough or something. So if we actually look at the waveforms, the yellow is obviously the triangle wave from that oscillator, the orange is the potential divider between the thermistor and the resistor, and the green is the output of the MOSFET. So this is roughly about sort of nearly 24 volt full scale, so we can see that we've got 12 volts on the MOSFET turning it on. Our reference is well above the triangle wave, so yeah, that's just static. Now if I stick the soldering iron near this thermistor to heat it up, you'll see that reference voltage. You'll see that reference voltage starts to come down, and as soon as it comes down to the level of the triangle wave, it's now turning off the output. The reason for that slow rise time is that because the MOSFET is being driven by that 10k pull-up resistor, that in combination with the MOSFET gate capacitance causes this slow rise, and that's intentional, just so that the load isn't turning on and off very rapidly, which could cause noise. So it's like a sort of soft switch on, which just reduces the rise time on the actual current. On the bigger one, the lead current is about 700 milliamps, so you don't want to be sort of switching that on and off, you know, within a microsecond or two. So that resistor just gives you that slow rise, which just makes it switch a bit more softly. So as it cools down, we're going back to fully on. And so with the leads, if I just put the soldering iron near that thermistor, so I'll turn the voltage down quite a lot just to reduce the brightness for the camera, so that just drops down. And so in practice it will never actually go off, because it will reach a thermal equilibrium with the heat from the LEDs on that thermistor. So in practice it will just dim down to the point where it just strikes a balance. So in practice, you know, it will dim slightly and you probably won't actually notice it, because obviously these things are sort of going on and off at various times. So one slightly dim one you just wouldn't notice. So it's a sort of graceful fallback rather than a hard cut off. And one other little detail, I actually used the 4-pin connector here. This was really just for mechanical reasons. I used the 2-pin at the top because there wasn't space for the 4-pin. It just gives them more grip, so that when this is being pre-assembled, it just holds these in slightly closer to the ideal position. It just makes it easier and quicker to assemble. So we could probably got away with the 2-way ones, but this just makes the whole thing mostly more easy to assemble. So it holds these in almost exactly the right positions, whereas the 2-pin ones were quite a bit more wobbly than that. Obviously the one on the top doesn't matter as much, and also the one on the top is a different type because it's a through board. So in terms of bill of materials, you know, all the ones on here are the same. This one couldn't be the same because it's on the opposite side of the board, so it doesn't really matter. That's a 2-way, and this just has to plug in there. We're not relying on that for any mechanical or alignment detail. And on the silk screen I actually put some text with a marker just to show them which way to bend this. The reason being that if you bend it the other way, you know, it might got too close to the lead or contacted a track. So, you know, again, trying to minimise the scope for a subcontractor to get anything wrong. The instruction is simply, you know, bend the tab in the direction of the arrows. So what is basically electrically a very, very simple job, there's still quite a lot of design work going into it in terms of things like uniformity and working on the assembly methods. So I hope you maybe found that useful. So a few tips. I really like these AVX connectors. I've used these quite a lot. They do all sorts of really cool connectors, and I was particularly pleased with that, figuring out this tab detail, because aluminium PCBs aren't actually that much more expensive than FR4. So, you know, in situations where you can use a single layer board and need some way of making some sort of assembly together, that's actually quite a nice method, just not needing any other fixings, just being really quick to put together and assemble into a nice solid unit.